Good evening everybody. So, today we will just see what are the other coordination numbers which can help us to know the minimum number of ligands which can bind to the metal ion, which is completely different from a system where only the metal ion is present as Mn plus. So, the presence of so many of these ligands, so they are either the neutral molecule or the charged one, particularly the anionic one, when they are in a typical geometry compared to the free one where we just simply write when we dissolve it a typical metal salt that it can have n or x number of water molecules surrounding the central metal ion, but what are the different ligands which can bind to the metal center and give some important reactivity pattern related to the metal ions if it is a 3D metal ion or related to the corresponding substitution and addition reactions. So, reactions we can expect from the ligand side and the electronic properties and other stereochemical properties which can be obtained entirely from the metal center. So, we just see that the second part of this coordination number, one typical example is in our hand, which is tetraphenyl phosphonium, which is of 4 in number attached to the palladium center, and that is very much similar to that of our nickel center, which is the corresponding tetracarbonyl species. So, we get some properties related to this center, and interestingly this one which is a nickel 0 system. Similarly, in case of this palladium system, where in place of these small molecules, carbon monoxide are comparatively small molecules compared to triphenyl phosphine. So, they are again 4 in number and palladium in 0 oxidation state, and this will give some important properties related to the palladium 0 oxidation state, because it can go from palladium 0 to palladium 2 plus, or sometimes the same center can go to some other oxidation states like the trivalent as well as the tetravalent oxidation states. So, in terms of the corresponding electron transfer behavior centered on this platinum, that means the d electron configurations which is now in the 4D level. So, how the reactivity of this particular center can be manipulated, and when we concentrate our attention on this particular aspect, that means the coordination numbers. So, in this particular case, if the coordination number is 4, what we can expect if there is a redox transformation from a complex which is palladium 0 having a coordination number of 4 is going from palladium 0 to palladium 2 plus, and further if it goes further oxidation to the trivalent palladium state or the tetravalent palladium state. So, what would be their expected coordination number? So, these are the two important questions what we can ask at this particular point, and we can get some informations or some answers related to this particular ligand, that means the nature what we have been discussing in our last class, that is a bulky triphenyl phosphine ligand is always will have some tendency to go away from the center if some entering group. So, incoming group is there which is attacking the palladium center and some phosphine can go. So, the steric bulk of this particular ligand system, which is the existing one, can also some important role to play to control these redox transformations if they are cycling between these two oxidation states. That means, if they are going from 0 to 2 plus and 2 plus to 0. So, we can expect that some of these important reactions where the palladium metal ion can take part and playing the corresponding catalytic role, then this particular system or this particular complex, the coordination complex in the 0 oxidation state of palladium can function as a very good catalyst in this particular case. So, if we have the tetrakis triphenyl phosphine palladium 0 compound, which can be very easily prepared through this particular reaction scheme, where we all know like nickel chloride, palladium chloride is little bit bigger one compared to the nickel in the 4D series of elements, which is reacting with two molecules of triphenyl phosphine giving a product which is basically a cis product. That means, the coordination number is increasing from say sometime this can be a corresponding species where is the polymeric structure of palladium chloride is known. In the solid state it can have the different structure, but this particular molecular species which is basically in cis geometry, that means two chloride and two phosphine groups are in adjacent positions, that means they are cis to each other forming 90-degree angles. So, chlorine palladium chlorine bond is 90-degree. Similarly, the phosphorus palladium phosphorus bond is also 90-degree. So, once we get this particular species, our target is that we will have a species where palladium will be in the 0 oxidation state and it will have 4 coordinated phosphine ligands. So, what thing we can do in the next step? The thing which we can do in the next step is the use of hydrazine, use of one particular reducing agent. So, hydrazine is well suited reducing agent which can reduce this palladium from +2 oxidation state to palladium 0, and we also add the extra amount of triphenyl phosphine, because already the molecule has only 2 phosphine triphenyl phosphine ligand. So, we have to provide 2 more, and the reaction stoichiometry is 1:2:2.5, where this particular hydrogen is broken into 2 fragments. One is the nitrogen gas is eliminated from there and hydrazinium chloride is forming. So, 2 molecules of hydrazinium chloride is also forming, abstracting this particular Cl. So, once we reduce this, so hydrogenium ion is playing double role in this particular reaction system, where this hydrogen is the source for its electron to reduce the palladium 2 plus to palladium 0, and at the same time when we reduce it to 0 oxidation state, it will not have any attraction for the chloride as their ligands. Instead, it has some surrounding available triphenyl phosphine groups. So, it will attract more number of triphenyl phosphine groups towards it, and this Cl minus will be taken away by the corresponding same hydrazine molecule, where the hydrogen is now behaving as a corresponding base in this particular system. So, we have this particular preparation based on this palladium chloride molecule, and is a very useful molecule. Just now what we are talking about, that if we can settle between the two oxidation states of palladium from palladium 0 to palladium 2 plus, and if they can go for some interesting reactions. So, this particular species is widely used in very important reaction in organic chemistry is the CC coupling reactions. So, in different organic synthesis, if we want to elaborate the molecule, if we want to increase the molecular structure by making new carbon-carbon bonds, which can be achieved by two reagents, one having one carbon center and another having another carbon center, but if we want to make a carbon-carbon bond between them, we can use this palladium triphenyl phosphine molecule as a very good catalyst. So, after getting that, we can have some more examples of catalyst as well as the corresponding coordination compound, where we see that we are just focusing our attention on a coordination number of 4. So, if we have a coordination number of 4, and just now we have seen that we can have the palladium center, then we can have any other metal center where we can go from a tetrahedral geometry to a square planar one. So, one such example is our Wilkinson catalyst, which is nothing but chlorotris triphenyl phosphine rhodium 1. Just now what we have seen one example where palladium was present as palladium 0. So, that was tetrakis triphenyl phosphine palladium 0, and what we have started from only that palladium chloride, that means PdCl2. So, as some intermediate product we got some PdCl2 P2, that means 2 triphenyl phosphine and 2 chloride groups are added to the palladium center, where the palladium oxidation state still remains in +2. But in this particular case, this is one other situation. Instead of going to the 0 oxidation state, we can go to a +1 oxidation state, and using the metal ion rhodium, and that is why the compound will have one chloride anion as the ligand, and 3 other positions are occupied by 3 triphenyl phosphine molecules. So, this is another example of a coordination complex where the coordination number is 4. So, this is the molecule where we will see that we have 3 triphenyl phosphine and 1 Cl. So, the Cl molecule will have 1 trans PPH3 molecule and 2 cis PPH3 molecule. So, this positioning of these groups are important for the different catalytic reactions what we can have, and some important reactions based on this is well known. Is a dark red compound, powder compound, we can make it from the corresponding rhodium chloride and the triphenyl phosphine as the ligand. And the preparation is also very much straightforward compared to that palladium compound, where we can use the rhodium trichloride. In case of palladium, we are use the palladium dichloride, but rhodium is in the cobalt series. So, cobalt, rhodium and iridium, what we all know. So, in that particular series, the stable oxidation state of rhodium would be +3. So, rhodium trichloride like cobalt chloride is available with 3 water molecules of crystallization, and when we react it with 4 phosphine molecules, this particular one is utilized for the reduction of the rhodium center. On the left hand side, this rhodium is present in the trivalent state, which is getting reduced to the monovalent state. It is rhodium 1 compound with the elimination of PPH3O and 2 HCl and 2 water molecules. So, triphenyl phosphine is going away from the medium as the triphenyl phosphine oxide leaving behind the molecule. So, again we have a molecule with a coordination number of 4 and which is square planar one, and it has long been known as a corresponding useful catalyst for alkene hydrogenation. So, it has also some historical importance, which we all know that it can catalyze the corresponding hydrogenation reaction for different types of alkenes. This particular molecule is further reactive towards some aldehyde molecules also. So, when we react this particular reagent, that means Wilkinson catalyst, when reacted with any aldehyde RCHO, we get the corresponding trans RHClCO whole 2 molecule, where the RCHO has been converted to RH and one phosphine group has been eliminated from the system. So, in this particular case, whatever we have already the molecule is in the trans geometry. So, the phosphine group which is present with the transposition of rhodium. So, we have this is the phosphine, this is the phosphine. So, what was present over there as the transposition, which was also occupied by another phosphine molecule, but during the reaction with any aldehyde, it can be the corresponding benzaldehyde also. So, it is converting to, so RCHO is entering in the medium and the corresponding hydrocarbon is removing. That is why it is taking away this particular carbonyl function as the corresponding CO molecule, and this particular triphenyl phosphine also is leaving away. So, is basically a corresponding ligand substitution reaction. So, ligand substitution reaction is nicely taking place on this particular system, and we are not going for anything because the triphenyl phosphine, what is being removed from this particular position, was a neutral ligand and is now newly occupied by a carbon monoxide molecule, which is also a neutral one. So, the oxidation state of this particular center is not getting changed, which is still in the monovalent state. That is why it has the corresponding preference for the original coordination number of 4, and it will remain as a corresponding square planar molecule, and it is preferring the corresponding square planar geometry. So, no ligand additive reaction, that means both the phosphine as well as the carbon monoxide is not occupying the position around the rhodium center. Only reaction what is taking place over there is the corresponding ligand substitution reaction. So, it is a very nice example for the corresponding transition metal complex of carbonyl group, because the carbonyl clusters, all we have seen that case of nickel tetracarbonyl. Similarly, very easily we can make the corresponding carbon monoxide compound of rhodium in presence of triphenyl phosphine. And in terms of the corresponding structure, that means this is a 4 coordinated compound in trans geometry. When we will consider the corresponding isomers, we will discuss again in detail of the corresponding effect of the donor groups, what they are manipulating, what they are doing due to the presence of these two groups trans to each other as well as cis to each other. So, another example of compound in the same geometry we are now giving example for that is the Vaska's complex, which is structurally analogous. So, whatever compound we have, this Vaska's complex would be again a 4 coordinated square planar compound. And since these are the corresponding nature of these ligands, so 4 coordinated square planar compound, these are the two informations what we are getting from the Wilkinson's catalyst. But in this particular case also we see that we have a corresponding carbonyl ligand. So, 3 types of ligands are present in this molecule. The Cl minus, which was originally present with the metal salt because we are using rhodium chloride as the starting material. So, it is a chloride salt. So, Cl minus is still present, which is one of the ligand. Then we have reacted it with triphenyl phosphine. So, triphenyl phosphine is our second choice. So, triphenyl phosphine is coming as the second ligand to it, and then we are reacting this particular catalyst, which is the Wilkinson catalyst, where we have 2 types of ligands with any aldehyde, giving rise to a species where the system is changing from a compound which is a metal and AB type of ligands to another where we have A, B and C type of ligands. So, what we get a corresponding M A B3 type of compound, which is 4 coordinated and square planar, which is getting changed to M, and A is still there. A is the corresponding chloride one, and B3 is now B2, that means one phosphine is going away, B is going away, and the incoming ligand is the corresponding carbon monoxide. So, these sort of things are very useful and very good examples for the corresponding ligand substitution reactions, because whenever we have a A2 type of species, say what we have seen the case of palladium chloride, what we have taken, or sometime the metal as the 3 anion is A3 type, which is rhodium trichloride. So, from there basically how we can utilize the different ligands. So, A is already present over there, here A is already there. So, how we can use this particular molecule for the reaction with A and then reaction with C, and if possible with the reaction with D, such that for a square planar type of compound or a 4 coordinated compound, we can have a species like MABCD. So, this is the metal center and we can have 4 different ligands attaching to the system. So, let us now see what is that Vaska's complex, which is similar to that of the product what we are getting from the corresponding Wilkinson catalyst. So, is a yellowish green powdery compound which can be very easily prepared, and if we just see the 3 types of ligands present to this, which is the Cl, the carbon monoxide and the triphenyl phosphine. Only difference is that now you have the iridium one. Instead of rhodium, we have now the iridium as the corresponding metal ion, and the geometry is again trans. So, if we have A, B and C type metal complex with 4 coordination number, that is why whatever product we are getting from the reaction of the Wilkinson catalyst with any aldehyde, which will be very much similar to that of our Vaska's complex, because this is a very important compound, very interesting compound to study, and it has again some historical importance. So, is getting instead of rhodium what we have just now seen, then the transposition of Cl is occupied by carbon monoxide and we have 2 triphenyl phosphine groups. And this has some other property which is related to the nature of the iridium, what is not observed in case of the presence of rhodium, so iridium compound which is there, so it can also react further for some addition reaction with molecular oxygen. So, like hemoglobin and myoglobin, this particular center is also have some affinity to react with molecular oxygen. So, O2 can be a very good ligand to the Vaska's complex, which is not possible, which we are not getting with the corresponding rhodium compound. So, that information is also very much useful to us, because for some catalytic reaction already we have seen that this is the product what we got from the reaction of any aldehyde to that of our Wilkinson catalyst. So, Wilkinson catalyst was already a catalyst, and that particular system giving rise to corresponding iridium analog, and iridium analog, if it can activate with the dioxygen molecule like myoglobin and hemoglobin. So, we get some species, some catalytic species where iridium is activating the dioxygen molecule. So, people have studied long for this type of molecules where we can go for some oxygen transfer reaction or oxygenation reaction based on the iridium, because whatever we are getting, that dioxygen molecule should definitely be activated through the corresponding coordination to the iridium center. So, that gives us and that opens up some important area of research, study and understanding, where the iridium center is utilized as a catalytic center and which can activate the small neutral molecule, which is very important, like dioxygen molecule. So, if dioxygen is getting converted to the superoxide species or the peroxide species through some electron transfer, we can get some of that type of information from this molecule itself, where the molecule is a very simple one with very simple coordination number of 4. And this particular species, like that of the previous compound where we have been preparing the corresponding Wilkinson catalyst from the rhodium chloride, similarly we can now take iridium chloride, but now instead of taking any aldehyde to the system, now we directly react this particular thing with triphenyl phosphine and dimethyl formamide, which is a very useful solvent, organic solvent, non-aqueous solvent well known to us, which is dimethyl formamide, which is a amide dimethyl amide of the formic acid. So, it is a DMF, this molecule is DMF to us, and C6H5NH2 is also given, which is the aniline molecule, and that aniline molecule, like our hydrogen molecule in the previous case, is being utilized as a base. So, we have IRCl is already present, one Cl is already remain there, CO is derived from this particular species, that means the DMF, that means from the solvent itself the CO is coming, and the corresponding triphenyl phosphine of 2. So, 2 molecules of triphenyl phosphine are going to attach to the iridium center, and what will left behind will be the corresponding amine, the free amine, the dimethyl amine as its corresponding chloride salt. So, dimethyl ammonium chloride will be formed over there, and the chloride will be taken care of from there, and aniline what is added over there. So, aniline is also another base. So, aniline is also forming the corresponding anilinium chloride C6H5NH3Cl, which is anilinium chloride, and the triphenyl phosphine basically is utilized for the corresponding reduction reaction of iridium +3 to iridium +1, and that for that purpose one molecule of triphenyl phosphine will be converted to triphenyl phosphine oxide with the elimination of 2 molecules of water. So, this is basically a very straight cut reaction and a single step reaction, because in the previous case what we have done with the rhodium trichloride, we have reacted with triphenyl phosphine and we got the Wilkinson catalyst first. Then Wilkinson catalyst was reacted with the aldehyde molecule to get the corresponding analogous compound of Vaska. So, further of this particular coordination number, we can take the use of the corresponding bidentate ligand. So, when we have been talking about several bidentate ligands, one good example what we have seen is the acetyl acetone, which is CH3 CO CH2 CO CH3. So, it basically go for enolization and the ketoenol tautomerism can give us some bidentate or donor mononegative ligand. So, this after deprotonation, this will give rise to some OO minus ligand. So, in a very simple and straight cut way, we can have any metal center like palladium, like nickel, like platinum. So, is also true for copper. So, when it is copper, we get the OO1, which is abbreviated as ACAC ligand, which is acetyl acetonate anion. So, two of these acetyl acetonate ligand will give rise to the corresponding coordination to the metal center. So, this gives us some other important opportunity to study these bidentate ligands. One good example we have already seen is the ethylene diamine. Similarly, if we start from any alcohol, so that can be derivatized basically. So, any alcohol, say ethanol, methanol, propanol, butanol, anything, if we react it with sodium hydroxide and carbon disulfide, we basically end up with some interesting ligand of bidentate nature, which is sodium xanthate. So, sodium xanthate is formed and we have the sulfur donor groups. Sulfur donor groups are bigger atoms, and these bigger atoms basically can go and bind to the metal center. So, if we add simple nickel chloride, it gives rise to the corresponding nickel compound of this type, like ACAC, this ACAC type of compound, but in this case we have both the sulfur groups attached to it. So, it will have the xanthate sulfur. Similarly, if we take instead of alcohol, if we take the corresponding amine R2NH, what we will be getting by doing the same type of reaction, we will be getting the corresponding dithiocarbamates. Similarly, one good ligand we can derive from all these things, whatever we are talking over here, is that if we have the acetyl acetone, which will abbreviate as ACACH and reacts it with hydrogen hydrate, we get the corresponding dimethylpyrazole unit. That means, here we have the NH group. So, this is NH. So, you have the NH function over here, and this NH function, if we can further modify like this transformation of O minus to the corresponding xanthate to R2NH to dithiocarbamate, we get the corresponding ligand as the corresponding pyrazole base 3,5 dimethyl pyrazole, which is nothing but 3,5 dimethyl pyrazole. So, 3,5 dimethyl pyrazole based ligand we are now having, and what we are just talking about this particular coordination, because this is a different one where we will just see, we will just give some example in our coming classes, which are known as ambidentate ligands, because we can have the donor groups available on this particular system is N S S. So, here the metal complex what we are getting through the use of xanthate is the corresponding sulfur sulfur coordination. Here if the same backbone is utilized, this SS bond is utilized here. So, you like this here we can go for the corresponding nickel coordination, but if this nitrogen is utilized for the coordination, we get a different type of compound. Say if we react with nickel, it will get the corresponding bis compound. So, nickel will be attached to it, and now two of these will be attaching to the system. So, we will have a coordination number of 4 in our hand, and already what we have seen that we can have a situation that this particular coordination can give rise to a tetrahedral geometry and a square planar geometry. So, and these are well known fact that one of the species what we have seen in case of nickel chemistry, the coordination chemistry of nickel 2 plus will see that in this particular case tetrahedral, which is a spin triplet state and which is a spin singlet state in case of a square planar geometry. So, the magnetic moment, if we can measure, the magnetic moment can differentiate these two geometries. That means, whether we have a corresponding coordination geometry of tetrahedral structure or a square planar structure. But in this particular case where the ligand is NS type, and we will find that something, that means when we have some corresponding magnetic moment which is in between the square planar or the tetrahedral, because in case of the tetrahedral which is a spin triplet situation, we have a magnetic moment of 2.84 Bohr magneton, and case of square planar it is 0. But if we have some intermediate magnetic moment, then we can expect that we have some other geometry which is in between a square planar and a tetrahedral one. So, what we see that the tetrahedral one is basically, if we just consider this the tetrahedral one. So, we can have the same ligand what we are utilizing, the pyrazole dithiocarbamate, and if it is square planar, is a trans one, it can be also the cis variety. So, what we see that these two planes, these coordinating planes, when we consider them within a cube, where the nickel is sitting at the center of the cube and these alternate coordinates are occupied by these groups. So, if these two coordination planes are 90° to each other, then we get the corresponding tetrahedral geometry, and if these two planes basically these two corresponding nickel nitrogen sulfur planes, if they are coplanar, it would be 0° and we have a square planar geometry. So, now in between we have the corresponding other distortions. So, it is basically going from 0° to perpendicular one. So, one plane will remain in the plane of the paper and this plane will go perpendicular to the plane of the paper to giving rise to a 90° orientation. So, for some in between geometries we have a corresponding structures as the D2D geometry, and this D2D geometry is basically varying from 0 to 90°. So, within a coordination number of 4 situation we can have a magnetic moment of 0 to 2.84 mu b, and if we can routinely monitor the corresponding magnetic moment, then we can have some indication whether we have a square planar geometry in the left or a tetrahedral geometry or some intermediate positions. So, in case of copper we just can have the corresponding situation for the copper 2 compound. This is basically if it is a neutral compound, we have a corresponding copper compound where copper is present in the bivalent state. But some more compound like the reduced form of copper which can also be stabilized in the cupra state. So, copper acetyl acetonate, which is very not easy to make that particular compound, is also because it is air sensitive and oligomeric species, because it can have some more number of species within a same molecular fragment, and in organic chemistry is a very useful reagent for Michael addition reactions. So, what we do for any kind of these organic transformations, for those reactions in a single pot we add the copper 1 salt, any copper 1 starting material, and the acetyl acetone as the ligand, but the most reactive species is the corresponding copper 1 acetyl acetone compound. And some of these informations and all these geometries are to be available in the inorganic chemistry by Messler and Tar. So, next we can move on to a coordination number of 5. So, if we can have the corresponding coordination number from 4 to 5, what we see that we will just talk about the corresponding basic geometry, which is the square planar one. Now, we will take the square planar one. So, we have one bond, second bond, third bond and the fourth bond. So, this coordination number, if we have a 4 bond already to us, so we will add up only 1. So, if we can have a situation where we can have a 1 pyramidal interaction. So, basically is a square pyramidal geometry which will have a coordination number of 5. Similarly, all we know that another important geometry which is also possible for simple inorganic molecules also, it is also true for the corresponding coordination compound, is the corresponding trigonal bipyramidal geometry. So, this is square pyramidal and this is TBP, the trigonal bipyramidal. And these two can also be interconvertible to each other, because the positioning of some bonds are only different, but we can move from one particular arrangement to the other by through some movement of these bonds. So, one such example with a inorganic example, typical inorganic molecule, not a coordination compound, is PCl5, the phosphorus pentachloride. And this phosphorus pentachloride will remain only in a trigonal bipyramidal geometry, and this trigonal bipyramidal geometry will have some differences between these. So, we have one type of phosphorus chlorine bond which is in the plane where the chlorine phosphorus chlorine bond angles, we have 3 such bond angles which are 120 degree, and then another bond which is in the apical side. These 3 are in the base of this particular trigonal plane, which is a trigonal plane. So, trigon, and these 2 are in the bipyramidal side. So, it is one pyramidal side and the lower is the other pyramidal side. So, these 2 are quite longer at 2.14 angstrom, and this is 2.02 angstrom. So, these phosphorus chlorine bonds are longer compared to the other 3 phosphorus chlorine bonds in plane. So, this is a classic example of a coordination number of 5 in a geometry of trigonal bipyramid. So, we have 2 possibilities, one can be the square pyramid and other would be the trigonal bipyramidal one. So, we can have a typical example which we all know that this particular species can be made where the cation is a particular complex species as well as the anion. Here the cation which is surrounding the chromium center by 3 ethylene diamine molecules is basically the octahedral one, and that we will discuss very soon after coordination number of 5. But what about the anionic part? The anionic part, which is a different one, which is NiCN whole 5 species. So, Ni is bipositive, which have a charge of 2 plus, and cyanide is balancing with 5 charges, and these 5 charges will give rise to a overall charge on the anionic part as 3 minus. So, this particular compound chromium should definitely be in the trivalent state. So, in this particular species, which we can have by gathering more number of cyanide surrounding the nickel, has a coordination number of 5. So, not in the cationic part, but in the anionic part we have a coordination number of 5. So, this is a classic example of a coordination complex where the cationic part and the anionic part has 2 different metal centers, and they also have 2 different coordination geometries and the coordination numbers. So, this is well known fact that how we can get this particular species, because we can substitute some other compound, that this particular cationic compound, the tris ethylene diamine chromium 3 cation or ion, can be obtained as its corresponding perchlorate salt or tetraphenyl phosphonium salt, but that can be substituted very easily if we can go for the corresponding pentacyanonickelate salt. So, nickel we all know is very easily reacting with cyanide, then we can go for further reaction with cyanide, and this is a well known compound to us, this particular compound as the corresponding square planar compound, which is orange red in color, and this orange red compound can further react with another Cn minus to give us a deep red compound of nickel in a trianionic species form, which is deep red in color. So, when this anion can go and substitute the corresponding chlorides of this salt, we get a compound where we get the typical example of a corresponding coordination number of 5 in the anionic part of the compound. Similarly, this is one more example of this, the nickel with 2 cyanide and 2 phosphine type of ligand. So, this is one more square bracket is there. So, we have the triphenyl phosphine of this there is 3 triphenyl phosphine and 2 CN minus groups are attaching to it. So, this is another example of a molecule where we have a coordination number of 5. So, it is not a typical triphenyl phosphine type of molecule, but is a substituted triphenyl phosphine. So, what we see that so far we have discussed so much about the triphenyl phosphine, but as we have seen that it has a very standard cone angle which is 145 degree and which is not always very easy to give rise to some molecules. So, we can substitute this triphenyl phosphine group, say, so 2 of the triphenyl phosphine groups can be substituted by OET group. So, this is also another triphenyl phosphine with 2 phosphine groups substituted by OT molecule. So, any molecule of this type which is MCl2 P3 will have a coordination number of 5. So, most of these types, so we can have this or MCN2 P3, which is the present example where M is the nickel, where this M can be a different one, which is well known RuCl2 triphenyl phosphine, and this we are getting this NiCN2 PPH OET whole 2 and whole 3. So, this basically gives us an important geometry of the nickel center, where we find that, because just now we have seen that the reaction of nickel 2 plus with Cn minus. So, this Cn will come first and will bind to the nickel center like C triple bond N. So, this nickel cyanide is well known to us. If we add further Cn, it will give the corresponding square planar geometry. But in case of this phosphine, so it gets simply getting some reaction where nickel cyanide can be reacted with this special type of phosphine ligand, is that we have these 3 positions like this, and we will have now this PPH OET whole 2 as the ligand. So, we have a corresponding geometry of TBP. So, this is also true for the ruthenium and some other type of compounds, where we will see that the phosphine groups which are present basically occupying some of these positions where we get this particular. So, the repulsion is there still because they are 190 degree apart, but in this particular case they will be 180 degree apart, but still they will not go for the corresponding species, because the nickel can have the possibility of getting the corresponding compound as NiCN2 PPH3 too, because the phosphine, these phosphine groups are the neutral ligand. But when they try to expand their coordination number from 4 to 5, they basically go for the corresponding coordination number of 5. So, this is a good example for a coordination number of 5. Similarly, if we can go for another good example is the Vanadyl species, where we all know that the vanadium compounds, unlike our copper compound or nickel compound, where ACAC is the acetyl acetone ligand, where we just now we have seen that acetyl acetone is basically binding towards the copper center, giving a coordination number of 4. But if we have some situation where already the corresponding oxo species of the metal center, the Vanadyl species is present, the Vanadyl species, so VO2 plus. So, instead of vanadium 4 plus, so tetravalent vanadium, since it has some affinity for oxygen atom, which can form very easily the corresponding Vanadyl ion. So, this Vanadyl ion having a dipositive charge will be very much useful or very much equivalent metal ion species like that of our copper 2 plus or nickel 2 plus or cobalt 2 plus. So, just now what we have seen that the copper 2 ion can bind to 2 acetyl acetone molecule, giving rise to a bis compound with a coordination number of 4. So, if the same Vanadyl ion can bind in a similar fashion with 4 of the oxygen atoms of 2 acetyl acetone molecule, we get a corresponding VOACAC 2 molecule. So, we have the VOACAC molecule which can be directly obtained from vanadium pentoxide. This is the acetyl acetone molecule. So, reaction of this particular species is basically giving us the corresponding compound as the corresponding Vanadyl acetyl acetone, and we have the oxidized form of the acetyl acetone one part, and the molecule is a very useful one where this is the vanadium center and we have the vanadium oxo bond and 2 such acetyl acetone ligands are attached to these 2 points. So, it is basically a square pyramidal geometry. So, the other geometry what we are getting over here is the corresponding geometry as the square pyramidal one, and which is little bit distorted towards this vanadium oxygen bond, because this vanadium oxygen bond is a double bond and this vanadium is little bit above the corresponding O4 plane. This is the O4 plane and which will be little bit lifted towards the vanadium oxygen bond due to the strong vanadium oxygen double bond, and it will be above the corresponding O4 plane. And this particular molecule has some catalytic activity and all these, and sometime it can also react with pyridine or amine type of donor atoms to expand its coordination number from 5 to 6. So, next day we will discuss how we can move from this coordination number of 5 to a situation where coordination number would be 6 and other regular geometries where the coordination number is 6 and above. Thank you very much.